All right, well, it's 9 a.m. Good morning, everybody. Welcome. Thanks for coming. Wanted to do a little bit of a review for the exam that's coming up. The exam opens today at 10 a.m., right after we're done here, and it'll be open until the end of day Friday. We won't be having a synchronous session on Thursday. Because we'll have that'll give you a little bit more time to get up and take the exam. But I will start to post some things for the following Tuesday. So we're really just focused on making sure everybody gets to campus, gets into KiteTester, and takes the exam for the rest of the week here. The topics for the exam, if you open up our Exam 1 review sheet, I've got a list of the topics that we've covered so far, as well as what I expect you to have gotten out of those topics. So you can read through there. We'll go through a little of those here in just a minute. I've also listed the activities that we've done there at the bottom and what I think the main point was for those activities, so you can go and review those activities and make sure that you send me any questions you might have on those. And then also the Smart Work chapters 1 through 5, which is our first 4 assignments, right through here all the way down to light and telescopes and solar system formation. So these first 4 assignments are the ones that you'll be wanting to look at. As far as tips and strategies for preparing for the exam, what I generally do is I look at my homework and activity first, because that's the stuff that we've been focusing on, and then I look at those things and go back and look at the lecture notes, watch some lecture videos on the topics that relate to those or things that you might be struggling with, and then I go and look at chapters of the book that might have more detail on those areas. And doing that in order just kind of helps you build a scaffolding. The thing about going straight to the textbook is there's a lot more information in the textbook than you can really hope to digest all at once. So it's nice to have some way to structure what you're looking at. But anyway, that's what I suggest. Let me just run through these topics here real quick to see what we've covered so far. We've done quite a bit over the last few weeks. We started off with the baloney detection kit, which was identifying our ability to detect logical fallacies and the types of logical fallacies we might run into. And this is just as we explore more ideas in astronomy, we want to be able to identify which ideas are valid and which ones are not, at least scientifically. We moved from that into scales of the universe, worked at understanding what the scales of the universe are in that activity, and really what I want you to get out of that is not so much the mathematics behind it, but just a really strong sense of the vastness of the universe. And so if you've done your scales of the universe activity, you'll note that there's the challenge of getting the solar system on a map of campus and still being able to see where all the planets are, and noticing that you can't see their sizes when the scale is that large. And also being able to make comparisons at different scales, so that you can, in your mind, if somebody tells you the relative sizes of things, you can kind of picture what those really look like. So that's what we did for scales of the universe. We worked on finding things in the night sky, primarily understanding coordinate systems in astronomy, how we use the altitude-azimuth coordinate system for local observers, and the right ascension declination coordinate system for observing across the globe if we want to share our observations with other people. And we learned how to tell the difference between those coordinate systems, as well as things like the ecliptic and the zenith and the meridian. And there's some vocabulary in there you want to familiarize yourself with, because we'll be seeing that as we go on. Next, we talked about cause of the seasons, identifying the primary cause of the seasons, which we all know is the tilt, but understanding that the tilt causes variations in the length of the day, as well as the intensity of direct or indirect sunlight, which is the thing that causes seasons on the globe. And as far as the seasons are concerned, understanding how changing some of those parameters, like changing the tilt or changing the eccentricity, would vary the seasons that we would see on a particular planet. And for that, you would want to go back to your cause of the seasons activity to see how that works. After that, we moved out of the celestial mechanics part and moved into talking about light and understanding the nature of light, the wave nature of light. We also determined the temperature. We found out we could determine the temperature of stars simply by looking at their color, which was a pretty powerful tool. Be able to look in the sky and tell the temperature of an object just by its color, by looking at its peak wavelength. And then we also talked about the relationship between the color, which is the temperature, and the luminosity and the size of a star, and how we can use those three properties to relate to one another to figure out stuff about the stars. We had a little introductory video on types of telescopes. We basically talked about the two types of telescopes, a refracting telescope and a reflecting telescope. And we also saw some of NASA's telescopes and what we're doing into the future. After the part on light, we moved into laws of motion, looking at Kepler's laws, which talked about the sort of mechanics of how orbits worked, these elliptical orbits where you had objects that moved faster when they were closer to the sun and slower when they were further away. And then we combined Kepler's laws with Newton's laws to get some really strong predictive ability to look at gravitational systems like the Earth and the Moon, and being able to see how that motion was determined by the gravity of the objects, this force of gravity that interacted between them. And so we also use the force of gravity to measure the mass of the Earth in our activity. So those are kind of the basic concepts that we've been through and how they tie together. As far as the activities are concerned, you can see where those fell on that list of activities. We had the scales of the universe activity, we had defining things of the night sky activity, cause of the seasons, the phases of the moon where we were practicing sort of projecting 3D motion onto a two-dimensional plane. We measured the mass of the Earth using gravity, and I hope you saw the sheet I posted in the announcements that showed that we measured the surface gravity of the Earth and the mass of the Earth to better than 10%. That was pretty cool, all of us combined. And then we did an activity on solar system formation, which led into our exoplanets. I just realized there is something on here we're missing. We had our big discussion of exoplanets, so I'm going to have to change that. So let's do this real quick. I'm so glad we're doing this together. Let me bring up this. Document. And where are we here? Yeah, there was one thing I forgot in here, which was exoplanets. That's the coolest thing about all this. So the fun thing about exoplanets is that we used all of this stuff that we had just learned we used Kepler's laws, Newton's laws, and gravity to find planets around other stars. So I'll add that to our activity list here. Okay, so that's it. That's what we've got for the exam this time around. And I'll post this new study guide for everyone so they have all of this. And at this point, I'd probably just like to take questions and see if anybody has anything they would like to talk about specifically, anything you'd like me to cover or go over that you're having some problems with.
John, can you go over the 3 Kepler laws one more time, please?
Sure. Yeah, I'd be happy to. Let me go and grab that here. Pull up these. Yeah, let me get this. Well, we'll go through it this way here. Yeah, so Kepler, if you remember, Kepler was the guy who first suggested that orbits didn't go in circles, right? That was his main concept. And up until that point, circles didn't really match the data, but neither did the geocentric model, so we were kind of at a loss. And he decided that he'd try ellipses and see what happens. And here's a picture of an ellipse. You can go back and look at the lecture notes for that. But Kepler's first law is simply that the planets orbit in an ellipse. That's the first one. The second one is that because on this ellipse, sometimes you're closer to the star. If you look at this diagram here, if we always have the star at one focus, right? So sometimes the planet is closer to the star, sometimes it's farther away from the star. That gives rise to Kepler's second law, which is that planets move faster when they're closer and slower when they're further away. And if you remember, we called that the equal areas law, and that just meant that a planet here, since it's moving faster, sweeps out the same area than here, even though it's moving slower, the areas of those things are the same, because here it's moving slower but it's farther away, so this area is larger. Here it's moving faster but it's closer, so this area is the same as this one over here. So these two areas are equal, and then we call that the equal areas law. It might be simpler just to remember that you move faster when you're closer to the star and slower when you're further away. So those are the first two laws. The third law was the really important one. That was the one that allowed us to do some predictive stuff, because it compared the distance from the or the semi-major axis of the planet from the star to its period. So if you could measure the period, how long it took the star to go back to the same, or the planet to go back to the same place in space as it was before, then you could figure out how far away it was. And the period was really easy to measure, so this was a neat thing. And that was written mathematically like this, that the square of the period is equal to the cube of the semi-major axis. And this Kepler's law works for the sun, because we don't have any units in it. We need Newton to give us a version that will work for anybody, for any star system. But this was a fantastic tool, because we knew the period of Saturn and Jupiter and Venus and Mercury, but we didn't know their distances from the sun. So once we knew Kepler's law could tell us the distances if we knew the periods, then we suddenly got the scale of the solar system. And we did an example here where we took Jupiter, which is 5 astronomical units from the sun, and if I put that in and take the 3/2 power, which is I cube it and then take the square root, I get 11.2 years. So what Kepler could measure is he could measure this 11.2 years. He could just sit there, if this is the sun, he could sit there and watch Jupiter go around making observations until it came back to the same spot, tell how long that took. He knew that was 11.2 years, and from that he could figure out that the planet was 5 astronomical units away, which meant it was 5 times further away from the sun than the Earth was. And so that's what was cool about Kepler's laws, is that it allowed us to determine a pretty amazing thing, the scale of the solar system, simply by observing the period. And that's really the important things about Kepler's law. A couple other things I should probably mention that you might want to know about is the relationship of the eccentricity to perihelion. Right? Now, again, on the exam, I'm not going to worry too much about you calculating these things, because it's a limited amount of time, and I'm not too concerned about it. But what I do want you to recognize is that if I look at an ellipse, right? So here's my ellipse, and I have the minor axis and the major axis, and I have the star at one focus. Here's the star. This distance is called the perihelion, and this distance is called the aphelion. Right, this longer distance here. And how squishy this circle is determined by a parameter called the eccentricity. And that's a number between 0 and 1, 1 basically being a straight line and 0 being a perfect circle. And we can tell that the more elliptical the orbit is, the larger the difference there will be between the aphelion and the perihelion. So as you make the orbit more elliptical, you're going to bring the perihelion closer to the star and the aphelion further away. And that's written mathematically here. You can relate these things mathematically to the semi-major axis and the eccentricity here and here. And the perihelion has a minus sign because it's going to be smaller. Aphelion has a plus sign because it's going to be bigger. And if I took the limit of E equals 0, then both the perihelion and aphelion are the same value. If I take E equals 1, then I get basically a straight line. There's no orbit to speak of. So again, I'm not going to worry too much about the computation of these things, but I do want you to recognize how their distances are affected by the ellipticity of the orbit. Does that help with Kepler's laws?
Yes, that helps.
Okay.
Thank you.
No worries. Other things. And if Sandra, if I can't hear you, you can type in the chat window. Oh, phases of the moon. I see you. Right. Yes, I'm so glad you brought that up. That's perfect. Okay. So let's do that, because I don't know why, but phases of the moon is my favorite thing. Let's see. course, all these things are my favorite thing. Where is... okay, let's go back to this. Okay, so I had a couple of multiple choice questions which were directly out of your activity on the phases of the moon. And rather than go through, well, we can go through those in a second. They're answered in these slides. But what I want to do is start a fresh slide, and let's see if we can work one out from scratch. Okay, so the thing about the phases of the moon, once you know the order of the phases, and you have that list in your activity, the order of the phases going from the waxing crescent, right? So they go from, well, I guess in your activity it started from the waning crescent was the first one, and then that went all the way through to the new moon, and this is the order in which they happen, to the waxing crescent, to the first quarter, again in order, go to the waxing gibbous. By the way, gibbous, I believe, I think it's Latin for round or a hump. So if you think about, if you know any Latin, that might help. Waxing gibbous goes to the full moon, right? And so that's the first half of the cycle, and then it just repeats itself, except now it goes waning, right? So then we go to the waning gibbous. We go to the third quarter, and then we go to the waning crescent. Whoops. And then we go back to new. So this is our full cycle. Now when we did the activity, we showed these things in order, right? That's why we had those pictures on the very top of that activity, which show what the moon looked like in the sky in the order in which we see those things. And what you did is you found out that you could kind of model this thing by putting the Earth right here. If this is the Earth, we can put the sun off to one side, and then we imagine what we would have to do to get the moon looking like the waning crescent through these cycles. And so the waning crescent's a little bit hard to visualize, so what I usually do is, since I know this is the order of operations, I start with the easy ones and then fill it in as I go. So I know, for example, that a full moon, I have to be fully illuminating the moon, which means that I have to see the lit side of the moon completely. And so the only way, if you imagine, the sun's rays are coming out like this, the only way to see the lit side of something is to be on the side facing the sun. So that's the lit side of the Earth. And so if I put the moon here, there's always half of it lit, but the only place where I can see half of it lit is if it's exactly opposite of the Earth. Now, when I draw this on the sheet of paper, you think to yourself, well, wait, but the moon is blocking the Earth, or the Earth is blocking the moon. And that only happens every once in a while when they perfectly align. For the most part, they're a little bit off by a few degrees, and so we don't get a shadow of the Earth on the moon. We get just seeing the lit part of the moon. So you have to see a full moon, a fully lit part of the moon, you have to see it opposite of the sun. So this is full, right? The next easiest one for me is to put the new moon. Now the new moon is where I don't see the moon at all, so the only place I can see a moon where I can't see the lit side is if the lit side is opposite of me, right? And we call that a new moon. So that's the only places we can see either a fully illuminated or a completely unilluminated moon. And you'll notice that the same half of the moon and the Earth is lit all the time because the sun's in the same direction. All right, after I've done that, the next easiest ones are the quarter moons. And if you want to think about it, the full moon is kind of like a football game, right? The full moon is a half moon. That means we have first quarter up here, halftime, and third quarter, right? So they're called first and third quarter because they're the quarters of the way around the full cycle. So first quarter, again, I want to see half of the moon lit. The only place I can see that is here because I have to be exactly at a 90-degree angle to see half the moon lit. Down here, again, I want to see half the moon lit. That's the only place I can see half the moon lit, so that has to be third quarter. So those are the four easy ones, right? That tells us how the cycle goes. So that gets us our new moon, that gets us our first quarter moon, that gets us our full moon, and it gets us our third quarter moon, and then back to new. So we just have to fill in these waning and waxing gibbous and crescents. For those, you want to think about, since a waxing crescent is a crescent moon that's getting more illuminated, that means we have to go from new to quarter, right, to be more illuminated. And if I'm getting waxing means I'm getting more illuminated, crescent means I'm smaller than half lit, so that has to be here, right? It has to be right here. And again, half of the moon is lit, so from my perspective on the Earth, I'm just barely starting to see this side right here, right? So that's the waxing crescent. And by the opposite thing, if I have a crescent moon that's getting smaller, it still has to be between third and new. It still has to be between half lit and new, but since it's waning, it's getting smaller. So I put it right here. Again, the same side is lit. So this is the waning crescent. Okay. So that gets my waxing and waning crescents. Now I have to work on my gibbuses. I know they go on this side. The top part is waxing because I'm going from quarter to full. So this is my waxing gibbous. Again, same half lit. This is the waxing gibbous. And the only other place there can be the waning gibbous is down here, which looks like that. So that's my waning gibbous. So that's how I construct the phases by memory, right? As long as I know the order in which the phases go in, I can make this picture sort of just by thinking about how the moon looks as it goes around. And the nice thing about this is this not only tells you where all the phases are, but it also tells you the direction, because if I know that if I go outside, these are the order in which I see things, that means that I have to see them in order this way. So I go from waning to new, new to waxing crescent to first quarter to gibbous, right around like this. And so you automatically deduce that the moon goes around the Earth counterclockwise. Okay, so those are just the basic phases. I've got a little more I want to go through, but I just want to make sure, see if there are questions about the basic phases. The next thing I want to talk about are the how you determine the time and location if you know the phase. Sound good? Okay, we're going to move on to, all right, we've got the basic phases. Now let's move on to how we tell time, location, if we know the phase. Okay, so first of all, I'm going to go back to this drawing here. I'm going to draw the Earth. Here's the Earth right here. I'm going to draw the sun. Actually, I'm going to just put the sun over here because I want some more room. So I'm going to put the sun over here. It's just off the screen. Again, now to fill these things in, if I want to have the new moon, it's got to be between the sun and the Earth, so that's my new. If I want the full moon, it's got to be opposite. My quarter moons go up here and down here. My waning and waxing crescents go here and here. You notice how I always light the same side of the moon, and my waxing gibbous and my waning gibbous go here. Okay. So new, full, and I'll just abbreviate these things. This is going to be first quarter, third quarter, waxing gibbous, waning gibbous, waxing crescent, waning crescent. So again, looking at this, the top half of the diagram is waxing, the bottom half of the diagram is waning. I have my first quarter gibbous fulls on the left. I have my third quarter waxing, waning crescents, new moons on the right. Okay. So as long as you can tell me, as long as you can draw this diagram, you can tell me where the moon is in its orbit around the Earth relative to the sun. So if I say new moon, where is it? It's right here. Okay. If I say full moon, it's right here. This is all looking down on the north pole of the Earth. The moon is going around like this. Okay, so the phase tells you where the moon is in its orbit. The second thing you'd want to know is what's the location of the moon depending on what time it is. So those two pieces of information there, the time of day and where the moon is. If I know either one of those, I can figure out the other one. So for example, let's take the case in the homework where we had the person standing, say, on the Earth right here. Now you're looking down on the North Pole, which means the Earth is rotating that way. Okay, so if the Earth is rotating this way, it's rotating counterclockwise around the North Pole. So north is looking out towards you. I can draw a line at my feet, which represents the horizon. Right, so that's the horizon right there. If I look to my left, if there's a full moon, so this is my left hand. If I look to my left, I see the full moon. If I look to my right, I see the sun. Right, so the sun is on the right and the moon is on the left. But because I'm rotating counterclockwise, in a little bit of time, as I rotate like this, pretty soon the sun is going to go below the horizon and the full moon is going to be above the horizon. And we have a name for when the sun goes below the Earth's horizon, and that's called sunset. So that means this time right here has to be 6 p.m. Because the horizon is rotating like this, that means if I look to my right, I see the sun and then I don't. If I look to my left, I see the moon and the moon gets higher off the horizon. So it has to be 6 p.m. because the sun has gone underneath the horizon. By the same token, if I'm over here, right, my left and right don't switch around. My right hand is still west, right, which is sunset. My left hand is still east, but because I've rotated around, now my left and right are opposite. Because now I'm on the bottom side of the Earth. So this is now west, and this is east. Because now if I imagine turning my head all the way around, my right hand is still associated with west, and my left hand is still associated with east, but I've rotated upside down. So now we have the full moon setting because we're rotating like this. It's going beneath the horizon. The sun is rising, so that has a name. It's called sunrise. That's 6 a.m. Okay. So if this is 6 p.m. and this is 6 a.m., right, halfway between 6 a.m. and 6 p.m. is midnight, so this is 12 a.m. Halfway between 6 a.m. and 6 p.m. is noon. And you can just start to fill this clock in, right? Halfway between noon and 6 is 3 p.m. Halfway between 6 and 12 is 9 p.m. Halfway between 12 and 6 is 3 a.m. Halfway between 6 and noon is 9 a.m. And so now you have a clock, right? This clock going around, and the time is told by where your head points. So if you're standing right here and your head's pointing at 6 p.m., it's 6 p.m., 9 p.m., 12 a.m., all the way around. So now that I have that, if you know where the moon is in its orbit by its phase, and I tell you where you are on the Earth, you can tell me what time it is and where the moon is. So let's try one. I'm going to see, I guess I'm going to have to erase this here. I wonder if I can screen grab this. Try it again. See if that worked. All right, so let's escape out of here and do an example. Whoop. Okay, so we go to our pictures of lunar phases from our homework. This is exactly off of your activity. Here I have the moon is right here, and what phase is that? I don't know if anybody can shout it out. Full moon, right? It's so strange to do this online. If we were in class, you guys would just be buffeting me. You say full moon, it's the full moon. Okay, so that's the full moon right here. Full moon. Just put an F for full moon. Here's the sun over here. I draw my horizon. This is my right hand. This is my left hand. And we're rotating this direction, which means this has to be, since the sun is got to be setting because it goes beneath my horizon, and the moon has to be rising, it's going above my horizon. This has to be east, moon rise. This has to be west, sunset. What time is sunset? 6 p.m. Okay, so because you knew the phase, you could tell me what time it was. Okay. Now, if I asked you where the moon was in this picture, I would say it's on the eastern horizon, because I'm looking. If I look to my left, I'm going to see the moon on the eastern horizon. So the answer to this one would be the time is 6 p.m. and the location is east. Okay. We can do another one here. Whoops, I think that's the same one. Yeah, let's do this one. Okay, so here we have one where you're located here, again looking down on the North Pole. What phase is this? You know this phase because you know the phases of your moon. This has got to be first quarter from that diagram we had. This is first quarter. We are located right here if I draw my horizon line. Now once you've determined your east and west, right and left hands, they stay the same. So my right hand is always west and my left hand is always east. So that means that this has got to be west and this has got to be east, because as we're going around eventually we'll get to the point where the sun rises, so that has to be in the eastern direction. So here's first quarter. If I ask what time it is, what time is it? If I'm exactly opposite the sun, it has to be midnight. And since I've already drawn my west and east here, I know that the moon has to be located on the western horizon. Okay. So that is some examples from your activity. We should probably do one that's not on your activity, just real quick to see what that looks like. Again, I'm going to draw these phases one more time just because it's fun to do this. If I put the Earth right here, put the sun over here, you have three pieces of information. You have the phase, you have the location, and you have the time. So if I tell you that the moon is in a, let's do a waxing gibbous phase. So the moon is in a waxing gibbous phase. So we've got new, waning crescent, first quarter, waxing gibbous. So that means the moon is over here. So that's the first piece of information. And I tell you that it is located on the western horizon. So now we have to find out where you are. If this is located on the western horizon, then I say, okay, well I knew here, if I'm right here, west is this direction because that's the sun. So I'm going to put this on the western horizon, march myself over until I can draw a line that puts the western horizon in that direction. Okay, so here's where you are on the Earth. The question is, what time is it? So let's look at our clock here. We had noon here. We had 6 p.m. here, we had midnight here, we had 6 a.m. here, and halfway between midnight and 6 a.m. is 3 a.m. So if I tell you the waxing gibbous moon is on the western horizon, you can automatically tell me it's 3 o'clock in the morning. So that's a handy tool, especially if you happen to be outside at night without a watch. Okay, so does that do pretty well for your phases of the moon? Okay, so Sandra has a couple of questions, generic questions about the exam. Sandra, before I answer those, I'll tell everybody those near the end, but let me see if there are any other concepts people want me to look at first, and then I'll get to that. Any other of the review sheet concepts you want to go through? And
John, can you go over the telescopes one more time for me, please?
Oh yeah, sure. Yeah, I appreciate that question because I wasn't able to make that session. So yeah, let's go. In fact, I have a couple of pictures I can show you here. Let me just open these up real quick.
So, in the homework, there was a question that I was kind of confused with.
Yeah.
And it was asking why they were having a difficult time imaging I can't remember which telescope they were imaging, and why they were having the difficulties getting images.
Oh, that was the Hubble. Yeah, that was the Hubble Space Telescope. Yeah. So let me go over the two basic types, and then I'll get to the Hubble because that's an interesting story. So we have the two types of telescopes. One of them is the refracting telescope that uses a glass lens. So here's just your typical. This works like a pair of glasses that you put on your face, right? You've got a lens that bends the light into a focus that you can look at. the whole purpose of a telescope is to basically be a giant light gathering device. So the bigger the telescope, the better. So these telescopes are fine, but there's a point where they get too big and they don't really work too well. An example of kind of the biggest refracting telescope in the world is this one right here. It's called the Yerkes Observatory, and the problem with glass is you can only bend the light so much with glass, and so the only way to bend it more and to get more light is to make it bigger, and you make these huge long tubes when you do that. So this is a limit because you've got this enormous heavy piece of glass hanging on the end of this big long tube, and so you can only make them about, maybe a couple meters in diameter at most. So we switched to using something called a reflecting telescope, and that's what this is the type of telescope you'd probably make or buy if you wanted to become an amateur astronomer. People have a lot of backyard telescopes that look like this, and they're better because the instead of refracting the light, it reflects light. So you've got the light coming in, and it bounces off a mirror, right? Like this, so a little curved mirror, and then it goes to a secondary mirror that goes out to an eyepiece where you can put your eye and look at it. The nice thing about this is it puts the heavy part near the ground, right? So if the heavy part's near the ground, you can make it as big as you want because you don't have to hang it off at the end of a big long tube. The only drawback to these kind is that in order to use them, you have to put a little secondary mirror to pick off the light, so you get you do block a little bit of the amount of light you can capture, but you just make the telescope a little bit bigger, and that works out. So these types of telescopes you can purchase or make your own. They're not very expensive. In fact, the most common kind is called a Dobsonian, and if you go down to one of the telescope stores or the camera stores, you'll see these things around, and you can get pretty large ones for not that much money. We make enormous ones. These are the Keck telescopes in Mauna Kea, Hawaii, and just for perspective, let's see here. The loading dock for these guys is right here. It gives you kind of perspective of how big these telescopes are. So, if you imagine putting a truck right here, you'll get an idea of how big these things are. These are 10-meter telescopes. They're 10 meters across right here. And you'll notice that the mirror part is located close to the ground, and then the little place where they have all the sensors and the cameras and stuff are up top. So you put the light thing up top, you put the heavy thing down at the bottom. And the only reason it took us a while to do this is because we had to learn how to deposit aluminum on glass in order to get a nice reflective mirror surface. So this is how we build all telescopes these days, is these reflecting telescopes. Now the question you asked was about the Hubble Space Telescope, and this is the picture right here. Interesting story, when the Hubble Space Telescope was launched, it was launched to be serviceable by the Space Shuttle, and when they ground that mirror for the Hubble Space Telescope, somebody put in the wrong, they put in a minus sign where there was supposed to be a plus sign in the computer program that ground the mirror down, and so they ground it a little too deep. And it basically was the same thing as making a nearsighted telescope. The telescope, all the images came out blurry. And this was just a stupid human mistake. Somebody pushed the wrong button on the computer and then they didn't bother to check it. And so we had to send a corrective optics. Basically, we had to put eyeglasses on this thing in orbit. And we could do that because we had the space shuttle, and this was a serviceable telescope. So it went from being, I think they called it the turkey telescope because it couldn't see anything, to one of the best instruments ever made. They put in a corrective piece of optics, and it worked flawlessly. And in fact, this instrument is still working. It was launched back in the late 1980s, did most of its work in the early 90s, and it's still, I just went to the American Astronomical Society meeting, it is still the premier telescope that we use. So that's pretty exciting that they were managed to be able to fix it. Of course, now we don't have a human spaceflight program, so if it breaks, it's broken for good. The last thing I want to leave you with telescopes, though, which I think is pretty exciting, is this guy. Again, a reflecting telescope. This is one of the ones that is in the design phase. This is a computer animation or a computer rendering. But this thing is 30 meters across. So it's 3 times bigger in size than the Keck telescopes, and it's that means if it's 3 times bigger, it's has 9 times the surface area, so almost 10 times as powerful as the Keck telescopes. And this is the things that they're talking about building in the next generation of telescopes. Again, the design is the same as everything we've been doing. It's just bigger, and it has little segmented mirrors in here that they attach all together, and they have little motors to actuate them and make sure they can focus the light. But this should be happening in the next decade or so. Some pretty cool telescopes. But as far as the exam is concerned, if you can remember the difference between a reflecting and a refracting telescope, then you're probably good. Does that answer your question, Shay?
Yes, that's it. That's
Okay.
perfect.
All right. Anything else you want to go over?
Not right now, not for me anyway.
Okay. Well, like I said, I put this study guide on our website, and I added one thing to it because I realized I left off the exoplanet. So I'll put this corrected version up there in just a little bit. As far as the exam is concerned, back to Sandra's questions, the exam is going to be on Tester. I think it's 42 multiple choice questions based on these concepts. You don't have a time limit, so you can take as long as you like. The exam is open. If we go back to our website here, the exam, where is it? Yeah, the exam is open. It starts at 10 a.m., so in 19 minutes it opens up, and it will stay open until Friday at the end of day. So let me
We
go.
could take that test anywhere, right?
Any of the Davis campus, Ogden campus. You can even take it. I think you can take it at like the West campus, the one in Roy, up in Morgan if you want to. Like there's pretty much anywhere you want. And now, are any of you located more than 50 miles away? Okay, it doesn't look.
I'm not.
Okay, yes. So there's so it's not located more than 50 miles away. You can make other arrangements, but hopefully it'll be a pretty good. Won't be too inconvenient. Okay, so I just uploaded this guy. Let's make sure that's the right one. Yes, okay. All right, any other questions? So Sandra is asking if we're going to be able to use the Google calculator. You're not going to need to. Yeah, I wouldn't worry about that. Yeah, I like you to do math in this class, but I also recognize that an exam setting is probably not the best place for you to practice your more advanced math skills, so don't stress out about that. All right, anything else? Okay, well, good luck. I will be available via email, or if you'd like to drop by my office hours this week, you can do that. If you'd like to set up another time to chat, that's good too. Just let me know.